Okay. Hi, Walter. We are gathered here at the Josef Stefan Institute's Triga Mark II reactor, and we will show you first a short intro, and then Tanya will show you a live demonstration of our reactor. So,
Pulse in 5, 4, 3, 2, 1, fire.
Welcome to the Josef Stefan Institute. We are very honored to be part of this event celebrating the 80th anniversary of the first man-made sustainable fission reaction. We will show you a step reactivity change experiment to demonstrate the inherent safety of the Triga reactors. We are currently in the control room of the Triga Mark II reactor in Ljubljana. The reactor was built in 1966 and was originally equipped only for stationary operation. However, in the year 1991, it was reconstructed to be able to operate also in pulse mode. The nominal reactor power during normal operation is 250 kW. However, during pulse mode, reactor powers can go up to a gigawatt. The Triga Mark II reactor at the Josef Stefan Institute is mostly used for various experiments, irradiation of samples, training of nuclear power plant operators, and education of students from all around the world. Now follow me, we can go and take a look inside the reactor building. Now we will enter the controlled area.
now Tanya is going on the reactor platform, from where the reactor core will be seen.
Now we are at the reactor platform. The reactor Triga Mark II is a pool-type reactor. The core is placed inside the aluminum tank and submerged under 6 meters of demineralized water. Water serves as coolant, moderator, and biological shield. The tank is placed inside the concrete biological shield. The pool-type construction enables insertion of samples inside different horizontal experimental channels. And we also have vertical experimental channels. Inside different experimental channels, the samples of different sizes can be inserted. For example, this is a triangular channel. Sample can be inserted inside it and placed inside the core. The reactor power is controlled with 4 control rods. Their mechanisms can be observed here. The reactor power is monitored with neutron detectors positioned outside the reactor core. Now we can go back to the control room to perform the
The neutron flux of our reactor is well characterized, which is why our reactor is the reference testing facility for neutron radiation hardness testing for CERN. Now Tanya is closing off the lights.
For monitoring the reactor behavior, we will use the digital meter of reactivity, which calculates the reactivity from the measured neutron flux using the inverse point kinetic equations. In red color, we can observe the neutron flux signal. In green, the fuel temperature, and in blue, the reactivity. We can observe that currently the inserted reactivity is 0, which means that the reactor is critical. We will perform the step reactivity change by withdrawing one of the control rods. Currently, the reactor power is 400 watts, which is below the temperature feedback effects. We will perform the step reactivity change and observe the reactor behavior. Reactor operator, please withdraw the regulating control rod for 45 steps.
Okay, withdrawing regulating control rod. Control rod withdrawn.
Okay, we can see now clearly in blue the reactivity change, and in red how the neutron flux is increasing, and also now the fuel temperature in green, which is also increasing. And as the temperature increases, also the reactivity gets lower. And if we switch now to the reactor view, we can see how the Cherenkov light appears, and it will become stronger and stronger. And the Cherenkov light is very nicely seen in these holes, which are where there aren't any fuel elements, so the light can clearly be seen. And maybe Tanya can add more to it.
The Cherenkov radiation is the consequence of the charged particles traveling faster than the speed of light in water. With increasing reactor power, the fuel and consequently water start to heat up, resulting in the thermal movement of water, which we can also see. The natural convection is enough to cool the water in the trigger reactor. The unique uranium-zirconium hydride fuel used in the trigger reactors can withstand high temperatures up to 1000 degrees Celsius and has high negative temperature coefficient of reactivity, which makes trigger reactor inherently safe. When we increase the reactor power, we reach the point when the fuel temperature starts increasing, and we can observe the temperature feedback effects, which start to decrease the reactivity. In time, the reactivity drops back to 0, and reactor stabilizes on a new higher power level. This experiment demonstrated the inherent safety of the trigger reactor due to the negative feedback effects. This concludes our experiment. So we will ask the reactor operator to shut down the reactor and observe the time decrease of the signal.
Okay, shutting down the reactor.
This concludes our experiment. Thank you for joining us, and we look forward for the rest of the celebration. Thank you.